Hello and welcome to a video lecture covering the second half of lecture 27. In this second video for lecture 27, we are going to focus on section 13.2. In this section, we're going to discuss weight in the context of universal gravitation. So we're going to understand weight in a new way. Okay? So let's take a look at Newton's second law for gravity. Okay? So right here, I just have Newton's second law. So we could label that as such. All right. Just a reminder, not that I think you've forgotten Newton's second law, but here we have F equals mg. Okay, well, what form does F take now that we're discussing universal gravitation? Well, let's consider that. All right, so if I write F in the context of universal gravitation, it would be G, little m, big M. I'll discuss what I mean by that. And then radius squared. Okay, so I'm not going to relabel these, refer to the lecture notes, the marked up lecture notes from the earlier pages in this lecture. So, before page 4, and the first lecture video to remind yourself what the universal force equation looks like for gravity. Okay. So, but here, specifically, little m would be the thing that's being pulled on predominantly. So that's like a person or a small object, and then big M is the planet. That's the main source of gravitational attraction. R is just the distance between the center of the two objects. So if you're on the surface of a planet, R would just be the radius of that planet. Okay? So that's just Newton's law of universal gravitation, the force. And then, so that's the left-hand side of the equation, the F sub g. The right-hand side of the equation is still mass times acceleration. Specifically here, I'll label it as A sub g to call attention to the fact that it's gravitational acceleration. All right, and then we just solve for AG. Well, look what happens. We see that gravitational acceleration is independent of little m. It's actually independent of the mass of the thing that's getting pulled on. Okay? So then, when we solve for A sub g, we get the result that is the second equation. So then you can think of this as a universal form of gravitational acceleration. So universal form of gravitational acceleration. Okay, so now you see where it comes from, where we can get gravitational acceleration, and now you can see that you could be able to calculate this gravitational acceleration for any large object like a planet of mass big M, and a distance between you and that large object of r, often the radius, right? Okay. So this should be where that 9.8 meters per second squared comes from. Right? That we should be able to show that the gravitational acceleration that we've been using and taken for granted is in fact derived directly from the radius of the Earth, the mass of the Earth, and the gravitational constant. Okay? So that's our goal, definitely. Furthermore, that independence, right? Because we've always said, well, everything accelerates at the same rate. Well, now we see why, right? M cancels, little m cancels. Okay, so let's put this into practice in example 1. All right. So in example 1, we want to compare the gravitational acceleration on the surface of Earth to that on A, the surface of Mars, and the top of the cloud layer on Jupiter. And I give you the radius of Mars, the mass of Mars, the radius of Jupiter, and the mass of Jupiter. All right, and assume these accelerations are measured at the poles. More about that in just a minute. Or why we would have to make that assumption, okay? So let's go ahead and first of all do Earth, okay? So for Earth, we would have AG, all right? I'll call this AGE, and that's going to equal, okay? So we still have the same universal constant of gravity, okay? That's 6.67 times 10 to the negative 11. 6.67 times 10 to the negative 11, and that should be Newton meters squared per kilogram squared. All right, and then we'll multiply that by the mass of the Earth. Okay, So I don't list the mass of the Earth here, but I'm pretty sure that we used it in a previous example. So let's call that up. So let's see. Yeah. So we're going to use 5.972 times 10 to the 24. So 5.972 times 10 to the 24 kilograms. And then we'll just divide by the radius of Earth. So for that, we will use 6,371 kilometers, which would be 6.371 times 10 to the 6 meters to convert it over the meters. And then we got to remember to square that. Okay, so let's plug this into the calculator. Right, so now we should get 9.8, right? This is a good check that this number, we're not just pulling that 9.8 number out of thin air. Okay, so let's put the airplane mode. Okay, so negative 11 times 5.972 times 10 to the 24, and divide that all by 6.371 times 10 to the 6. Don't forget to square that denominator, and I get 9.81 meters per second squared. So there we have it. Gravitational acceleration on the surface of Earth. Nice. All right. All right. What about for Mars? Okay, so gravitational acceleration on Mars. All right, so same constants. Okay, Mars has a different mass, so significantly less massive. 3.39 times 10 to the, oh, no, that's the radius. 6.42 times 10 to the 23 kilograms. Again, 1/10 the mass, almost. All right, and then the radius is about 1/2, a little bit over a half. 39 times 10 to the 6 meters squared. Okay. All right, so now let's run these numbers. So 3.39, okay, and then 6.42 for our mass, and then don't forget to make it times 10 to the 23 instead of 10 to the 24 kilograms, and we get 3.73. All right. So that means that when you're falling on Mars, you would accelerate at not a third, but just over a third the rate that you would here on Earth. So in other words, you would feel significantly lighter, right? Because what is weight? Weight is normal force. That's mg, right? It's if you're standing on an unmoving floor, then your weight is just equal to mg. So then someone would have a weight that is whatever the ratio of 3.73 over 9.81 is, about a third, okay, or just over a third, right? So you'd weigh significantly less on Mars. People often talk about the moon. On the moon, you actually weigh about 1/6 what you do on Earth, because the gravitational acceleration on the moon, with the radius and the mass of the moon, gives you a gravitational acceleration on the moon that's about 1/6 of 9.81. But what about if you were up in the clouds of Jupiter, right? So in this case, you've got to imagine you're not in orbit. Maybe you're like floating in some sort of hot air balloon, right? So you're at rest relative to Jupiter, floating up in the upper clouds. And let's see, how heavy would you be? Okay, so J for Jupiter, same universal constant, because Jupiter is much, much more massive. Okay, it's also larger. So let's see, the mass here, 1.9 times 10 to the 27. Right, so 1,000 times more massive than Earth, 3 orders of magnitude more massive, and significantly larger radius, especially because it's less dense than Earth. Okay, though it's not the least dense planet. Saturn has that distinction. In fact, Saturn is the only planet with a density less than water. Okay, so let's plug in our numbers here. So we'll plug in the mass of Jupiter. 1.90 times 10 to the 27, our new radius, 6.99 times 10 to the 7, okay? About 10 times the radius. All right. Well, even though the radius is bigger and that you're sort of effectively further away from the center, and that will decrease gravity. The 1,000 times the greater mass means that your gravitational acceleration on Jupiter would be 25.9. So you would be uncomfortably heavy, right? You'd be over twice as heavy. It'd be difficult for you to move, okay? That's like experiencing 2 G's of acceleration, okay? It'd be hard to lift your arms. Possible. We're not talking, like 10 G's or something, but this would be, you'd be noticeably heavier, and that would affect everything you do. Okay. All right, so just kind of quick check there about thinking about what weight means and how, interestingly, it's different in different worlds. Okay, so now let's consider the idea about the pole, okay? Because when you're standing on the pole, like shown in this picture here, there's a lot of information in this picture, not all of which we need, but you're standing on the pole. In that case, the only force that you're experiencing is the gravitational force. If you're standing on a surface, then you experience a contact force, which is the normal force. So you have a normal force, gravitational force, represented here by W for weight, and those two forces cancel out because you're at rest, okay? So that's the full free body diagram when you're at the pole. When you're at the equator, you still have the same non-contact force, the gravitational force. You still have a normal force, but now you're accelerating, okay? So these forces would not sum to 0. They would sum to the centripetal acceleration of whatever is your centripetal acceleration at the equator, okay? Which we can find because we know the period of the day and we know the circumference of the Earth, right? So we know the distance you're covering, it's uniform circular motion, so we can find V. Once we find V, we can find the centripetal acceleration. Because again, you are not at rest when you're at the equator, okay? So the sum of forces is not equal to 0. If you're somewhere in between, then you would have a different centripetal acceleration because your velocity is dependent on the radius, of course, okay? And also, the vectors are no longer along a single axis, so you'd have to consider components. Okay. All right, so we won't worry about the middle case, but we're going to compare the percentage of your North Pole weight with what you would weigh at the equator. Okay. So I meant to copy over a solution for this one, but I'm just going to do that now. Okay, because I don't want to rewrite it, but I will go over the steps. All right. So here we have our axes for both cases. That's like what you look in the picture. So let me circle those. I'll zoom in a bit. So here I'm just defining positive y as up for the person at the pole. For the person in the equator, I'm also defining positive y as up because I'm going to do a separate free body diagram for both. All right, so let's do the free body diagram for the pole. So the F net, as I said, is just negative Fg plus the normal force, P for pole, right there, and that's going to be equal to 0. Okay, so a scale would simply read Fn equals Fg equals mg. Okay, and we know g here is just, well, it's 9.8, and we showed where that came from. Okay, at the equator, however, you'd still have the downward forcing gravitational force, you still have the upward facing normal force, and then you have m times AC. Okay, here the centripetal force will be pointing towards the center, so it's pointing in the negative direction. All right, because again, we defined positive y as the kind of the outward radial direction. The inward radial direction is defined as negative, hence negative AC. So the free body diagram will take a look like this. This is the form of centripetal acceleration. This is the only acceleration that that anyone would experience on the equator because there's no tangential acceleration. Okay, and anyway, we're only concerned with the net force in the y direction. Okay, so it's m squared, mv squared over r. But then we can, because it's uniform circular motion, we can set v equal to 2 pi r over t. 2 pi r is circumference, t is the period. All right, and that's because it doesn't change, right? The Earth is never slowing down or speeding up. And so this is just distance over time, right? Just definition of velocity, of least constant velocity. Okay, and so then we have 2 pi times the radius of Earth here, right? About 6.3 million meters. And here's the period in seconds, 24 hours in a day, 3,600 seconds in an hour, okay? Because of course the period is 24 hours, one day, okay? So that means that anyone at the equator is traveling 463 meters per second. Okay? That is their velocity relative to the center of the Earth. We're thinking relative velocities. Okay? They're absolutely in motion. Someone at the pole has a velocity of 0 relative to the center of Earth. Okay? Someone at the pole would still have a, angular velocity, but they don't have any translational velocity. Okay? So then I'm going to go ahead and plug this expression in for v, okay, and I square it, which is why it becomes 4 pi squared r squared over t squared, and that's just squaring this, okay, and that's all going to be over r. We see that one of the r's cancel, and so then our normal force at the equator simplifies. I'm going to go ahead and add mg to both sides, kind of like I did up here, okay, and so then this becomes my normal force. Okay, so notice that the normal force is reduced. Instead of just it being just mg, it's m times g minus this expression here. This reduction, of course, comes from the centripetal motion. The percent difference then is this going to be normal force at the pole minus normal force at the equator divided by normal force at the pole. Okay? Because I asked what percentage of your North Pole weight. So since I'm comparing to that since I'm comparing the North Pole weight has to be in the denominator. Okay, so then I plug in the expressions. The mg cancels from both of them. So then it simplifies quite a bit to this nice percent difference. Okay, of course that should be times 100. Let me put that in there. Make that obvious because I left that out and it looks like I'm not multiplying by 100 anymore, but I still am, as shown in the previous step. Oops. So this is still times 100. Okay, and so when as a percent, it ends up being 0.34%, about 1/3 of a percent lighter. Okay, so it's not a big difference. We probably didn't expect it to be a big difference. No one talks about how much lighter they feel when they travel to, equatorial countries, right? So yeah, it's not a big difference, but it is measurable, certainly. I mean, if you were on a digital scale that measured tenths of a kilogram, it would be a noticeable difference. If you took an object with you and weighed it, an object that didn't change mass, person probably isn't the best example for that, but some solid object, you took it at both locations, there'd be a noticeable difference. Okay. One way this matters is for rockets, right? Very expensive fuel, large object. It makes sense to launch rockets as low latitudes as possible. Now, because of the kind of the curvature, there ends up not being, it's not like a linear relationship. So as long as you're fairly far south, you're getting a lot of that centripetal effect, which is helping in the essentially things weighing less, thus easier to get off of the surface, maybe easier to get into orbit, easier to escape Earth's gravitational pull. More on that later. But you don't have to be all the way at the equator. You just have to be not that far north. Okay? But it'd be best to be right at the equator. Okay, so hopefully an interesting example, thinking about gravitational force, relating that, in this case, to centripetal force. And we're going to be doing that quite a bit more next week. We do a lot with centripetal force for orbits, so this is definitely kind of a precursor of things to come. Okay, so what else do I want to show you? All right, so yeah, we can definitely talk about, I'll leave 5 for practice, but twice as high, and then 6 I'll go ahead and leave for practice as well. So let's take a look at 3 and 4. See if I can copy those over. I think I have those ready to go. Maybe. Okay. Yeah. So these are the last 2 I wanted to show you. And again, I'm leaving the rest for practice. Don't look at the solution while we're over here. Okay. There we go. All right. Okay. So I'm going to go over these examples, and then that will conclude this video. All right, so example 3. The International Space Station, known as the ISS, is at an altitude of 435 kilometers above the surface of the Earth. This is called low Earth orbit. I find that interesting. Hope you do too. Is the apparent weightlessness of astronauts in the station explained by their distance from Earth's center and the formula for gravitational acceleration, right? Because R is definitely bigger. Does that mean that A is approximately 0 when you're that far? Probably not, because it's only 435 kilometers. It's not a big difference percentage-wise compared to the 6,300 and 70 kilometers from the center, right? So we can probably logically rule that out. And you might know that that's not why astronauts are weightless. If an astronaut was at rest at an altitude 4 times greater than that of ISS, which plenty of satellites are at, 1,200 kilometers above the surface of the Earth, what would their acceleration be if they suddenly started falling towards the Earth? Okay? Okay, so part A, big no. No, their weightlessness is because they are in free fall. Okay? So every satellite, including the International Space Station, is just falling. Okay? More on that later when we talk about satellites, but it's literally just falling. It is in free fall. And pretty darn good approximation of free fall because there's very little drag. That's why we have to be at a certain altitude, above about 200 kilometers, where that, we need to be at a point where the atmosphere is so thin that its effects are negligible. There's still gas molecules up there. It still matters. It makes a difference, but it's a very, very small difference. Okay, and then B. Okay, so now we're going to be at a distance of was at rest altitude 4 times greater than that of ISS. So so I go ahead and solve for A. Here I have the radius of the Earth. Here though it looks like I'm putting in the 4.35. So let's fix that. I think I must have changed the problem. So instead of it being 4.35, it should be, let's see. So if I take 435 and I multiply it by 4, that gives me 1,740, and that would be kilometers. If I convert that over to meters, that would be 1.74 times 10 to the, 10 to the 6. Okay? So yeah, so basically 1,740 kilometers, right? Because we're at 1,000 kilometers is a million meters because it's 10 to the 6. And so if we have 1,740 kilometers, that's 1.74 million meters. Okay? So if a satellite that is at that altitude above the surface is, you can think of that as being, well, if about a third of Earth's radius above the surface, right? Okay? Now, we'll talk about satellites that are much higher than that, but for now, that's totally a reasonable location for a satellite. So how fast would a satellite accelerate? So the idea there is that if the satellite suddenly stopped moving, if it stopped being in free fall somehow, maybe it just fired a rocket in the opposite direction it was falling and then brought itself momentarily to rest, well then it wouldn't be in the same sort of free fall, right? Because there's there's an acceleration down, but there's a translational velocity to the side. So if we were to do away with that translational velocity, the only motion then would be straight down, and objects then would just fall straight down. Okay? But how fast would they fall? Well, you saw the International Space Station has a gravitational acceleration of 8.6, right? Not that different from 9.81. What if we were up higher? What if we were up at the 1,740 kilometers above the Earth? Let's see. Okay. Right? So 6.05. So even when we're getting up pretty high above Earth, yeah, gravitational acceleration is still pretty significant. That you'd weigh more than on Mars, even though you're that far above the surface. So gravity does start trailing off. It reduces as you move away. But, of course, it only reduces as the square of the distance. So in order to get, let's say, a quarter of the gravitational acceleration, you would have to be twice as far. Okay? All right. So we got one more I want to show you. So example 4. The dwarf planet Ceres, this is the only dwarf planet in the asteroid belt, okay? And has a radius of 9.5 times 10 to the 5 meters. So it's 950,000 meters, so much, much smaller world. And it has a mass of 8.958 times 10 to the 20 kilograms, okay? What would be the weight of a 70 kilogram person on the surface of that world at either pole? if the planet was spun up so that a person of 70 kilograms had a weight of 450 newtons while standing on the ceiling of a cavern near the planet's surface at the equator, then what would be the length of the new Ceres day? So the idea there is if you turned the planet into a giant space station where it was spinning in order to create artificial gravity, how fast would it have to be spinning? Okay? And then what would be the period of that spinning motion? Okay? So let's take a look at part A. So part A, we're just going to find weight. Weight is just Fg, which is just going to be, okay, and again, we're finding weight here, not gravitational acceleration, which is why little m is included. All right, and so universal constant of gravity, mass of Ceres, mass of the person, radius of Ceres squared, they end up weighing 4.63 newtons. All right, and just to put that in perspective, because that seems really low, that's because look what gravitational acceleration is on Ceres. G Ceres is just 0.066. Wow, that's tiny, right? Because we were talking about how it's, quite a bit lower on Mars, you weigh third as much. Here, I mean, we're talking like, 3 orders of magnitude less. I mean, it's suddenly jumped up, like when you get to smaller worlds, gravity becomes negligible. I mean, think about this. This is telling you that something that is in free fall is going to accelerate 6.6 centimeters per second. Okay? Or a better way to put it, it's going to pick up a speed so if it's in free fall for 1 second, it's going to be traveling 6.6 centimeters per second after free falling for 1 second. If you drop something on Earth and you let it fall for 1 second, after 1 second of motion, it's moving 9.8 meters per second. Okay? Here, something's been falling for a second, it's still just like gradually falling. It'd be noticeably falling, right? 6 centimeters a second is noticeable, but it'd be like everything is just drifting down, noticeably moving down, but everything would be so slow. It's kind of amazing to think about, because you see like the moonwalk, but here you couldn't even walk. Like because walking requires gravity to pull your leg back down to the ground, right? So it's like it'd be frustrating, right? You'd lift your leg up, and then you'd have to wait for it to come back down, right? You could check your text messages while your leg's coming back down to the ground. Okay? All right. So part B, right? So sci-fi idea here, turning the planet into a giant space station. Okay, so here we want a net force to look like this. The idea is we'd have a normal force, we'd have a gravitational force. Okay, they're both pointing what I call the positive direction. So I have a different coordinate axis as opposed to the problem where we had the percent difference between your weight at the pole and the equator. So here, positive r is defined towards the center of the world, okay? Which means that all the forces are positive. Normal force is defined as positive, gravitational force is positive, centripetal force is positive. The reason the normal force is positive is because the person is standing on the roof of the cave. Of course, for them, it would be perceived as the ground because anything that you're pulled towards is perceived as ground, okay? So then I go ahead and solve for V, okay? So we plug in our values. Here we want a normal force of 450. Why 450? Well, because that's about half Earth's gravity. That's, kind of like, hey, let's have a space station that kind of simulates, recreates Earth's gravity, but we don't have to go all the way. We just have to get something where maybe you feel lighter, but you can still manage daily tasks, right? So that's why I felt 450 was a reasonable value, okay? Of course, on Earth, a person would weigh closer to 700 newtons, okay? And so then we have here the 4.63 that we solved for in part A. This would be their weight without the centripetal motion. All right, and so it turns out that they would, at the equator, require a translational velocity of 2,484 meters per second. Okay, it's pretty fast, okay? 2.4 kilometers per second. That world's really booking. All right, and so that would end up being a period of 2,400 seconds, and that's just, again, using uniform circular motion. So the circumference divided by the velocity in this case, because we're solving for the period. And so that means that Ceres would have to have a day that's 40.1 minutes long. I don't know what its current day is, but it's sure a lot shorter than that, because it turns out small worlds tend to, due to conservation of angular momentum, have smaller velocities, thus longer days. But 40.1, that's pretty fast, and you could think about how much energy would that take to spin up a world like that. Probably a lot. Okay? Then you need the moment of inertia series. Okay. So hopefully interesting stuff and a little bit introduction into the idea of weight in a more general sense, not just specific to Earth. Okay? All right, so again, example 5, where you just be considering a planet that has a certain fraction of Earth's radius and mass. And then example 6, where you're going to be kind of modifying example 2 with the difference between your weight at the pole and the equator. But here in the imaginary world, you're going to have a much more dramatic effect. So when you go to the equator, you wait. Let's see, you're able to jump twice as high, and you can of course think about the kinematics, what that means for what your weight must be. Okay, or at least what gravitational acceleration must be there. Okay, all right, looks good. So go ahead and try those examples if you get a chance, and thank you for watching.